Okay, so yesterday we were talking about closed loop control, and on the example actually last week's example, I showed you with some numerical examples that by applying feedback control we can improve the performance of a system. So if you remember these tables, if you apply open loop control, then even if you can have satisfactory performance under ideal conditions, when you have some things that are not accounted for in your design, these things can cause your performance to drop, and this performance drop can be quite large, as you see on this table. But by applying feedback control, depending on what type of controller we have, obviously, the performance can be changed. That's the critical thing, and it totally depends on the controller design anymore. So the first one is just the simplest controller you can have, simplest feedback controller you can have. It just consists of a single constant number. So you can, even with this simple controller, you can, as you see, reduce the effect of these disturbing effects. Okay, and by changing that number, you can improve it even more. So the controller design is the key factor there. Well, in fact, I don't know why you would do that, but you can use a controller to make the performance worse. So that's another thing you can do. Obviously, in most cases, you want to make the performance better, but if for whatever reason, if you want the system to behave in a worse way, you can achieve that as well by using in fact, a good example is these training aircraft. So I remember talking about this before. If you have an aircraft, by designing autopilots, you can change the characteristics of the aircraft. So you can make an unstable aircraft fly in a more stable way, or if you want to train the pilots to control a hard to control aircraft, you can achieve that by using the controllers again. So in that case, intentionally you make the aircraft fly in a worse way so that the pilots can be trained for that. Okay, so on this example, with the open loop control, there's well, the system is still controlled. You want to drive at a constant speed, and it does drive at a constant speed. It's just that the speed gets affected by a lot of factors. But I told you that for certain systems, feedback control is necessary. And without feedback control, you cannot control those systems at all. And as an example, I used this long stick as an inverted pendulum. So today I would like to start from there. So what makes feedback control necessary is a concept called stability. So I'm sure you all heard the word stability at different places, but in controls engineering there are some precise definitions for stability, and in fact there's not a single definition used for stability. There are different versions of definitions for stability, but the good thing is these different stability definitions are valid for nonlinear systems. So if you have a linear time invariant system, then all different definitions of stability merge into a single definition. So let me just start with one particular definition for stability. So in this first concept of stability, we talk about stability of equilibrium points. So this is not related to the system itself, really. It's just related to the equilibrium point. So a system may have different equilibrium points, and it may have different stability characteristics in each one of those equilibrium points. So obviously we first should define what an equilibrium point is. So let me read from here. Equilibrium point is a condition of a system where all the system variables are, well, zero. It says zero here, but it's not correct. It should have said constant. Okay, so all the system variables are constant, means if everything is constant, then all derivative terms should be zero, right? So the way to find equilibrium points is to set all derivative terms equal to zero. And when you find such a point, then that's an equilibrium point for your system. Okay? So mathematically, the way to find equilibrium points is the following. So first you take the differential equation of your system. So for a general nth order system, if the equation is given in this form, so all these derivative terms should be equal to zero. Right? These are all derivative terms. And for the control terms, you set everything equal to zero, as it's written here, and the values of the system variables, like the value of y and u, that satisfies these conditions, defines your equilibrium point. Okay? So these are the values of your input and output variables at the equilibrium point. Okay, so I think we should take a look at an example. Okay, so I'm looking for the pendulum system. So this is a simplified model of the inverted pendulum experiment from yesterday. So the equations for, or the differential equation for that system is this equation. So the output is the position of the pendulum. Input is the torque we apply. This is the input torque. So for the equilibrium point, so at the equilibrium point, all derivatives are zero. But if you look at the equation, we just have theta double dot, right? So we don't have any theta dot term at all in this equation. So this becomes equal to zero, and from there we get minus mg L over 2 times sine theta 0 should be equal to Tc 0. So when no external moment is applied, that means T sub C0 is equal to 0, the equilibrium or pendulum can be found from equating this term to 0, since Tc0 is equal to 0, and from there we get that sine theta 0 should be equal to 0, and from there we see that theta 0 should be equal to some integer multiple of pi, right? So if n is equal to 0, pi is equal to, or theta is equal to 0 is an equilibrium point, which corresponds to this upright position. So this is an equilibrium point. And another equilibrium point is when theta is equal to pi. So the other equilibrium point is this. And these are both equilibrium points. Okay. Okay, so that's what an equilibrium point is. Okay, so once we define an equilibrium point, we define the stability of equilibrium point as follows. So by the way, let me just add a slight note, a small note here. There exist different equilibrium points. If a constant if P sub C0 is not equal to 0, then the pendulum will be at different that can be found from the same equation. Okay, so if you apply a constant torque, then obviously that constant torque will hold this pendulum at some angle. So you can hold this here if you apply a force that will balance the moment on it. Okay. So you have these lecture notes. You can take a look at these other examples given there. So here it says an aircraft in steady flight can be considered to be in equilibrium. So if like the altitude of the aircraft, the speed of the aircraft, or the heading, all those quantities are constant, then the aircraft is in an equilibrium state. Okay, so that's what an equilibrium point is. And from there we define the stability of such point as explained here. So an equilibrium point is stable if perturbations given to the system at the equilibrium point causes the system to go back to the equilibrium point without any external input. So maybe I should add that statement here. The equilibrium point so if the system moves away from the equilibrium point, then it is an unstable equilibrium point. So consider a system at equilibrium point. If you somehow disturb that system, then if it goes back to the equilibrium point by itself without any external input, then that's a stable equilibrium point. If, on the other hand, it just moves away from the equilibrium point, then that's an unstable equilibrium point. Okay? And a very classical example used to demonstrate equilibrium stability is this example. So both of these points are equilibrium points, right? So you can place the ball here and it will stay there. all the derivative terms will remain 0. Similarly, this is also an equilibrium point. If you just place the ball very carefully here, and if you don't apply any forces, external forces to it, it will stay there. But if you consider the stability, then you consider the following. You take this ball, you just give it a disturbance or apply some perturbation to it. In this case, the ball will, with the help of the gravity force, it will go towards the equilibrium point. And if there's a friction here, it will oscillate a little bit, and then it will come to a rest at the same equilibrium point again. So that's a stable equilibrium point. Whereas if you consider this case, then disturbing this ball slightly will cause it to roll away from the equilibrium point. So that's an unstable equilibrium point, right? Bilmiyorum ki. Şimdi stagnation point neydi? Orada akış duruyor. Değil mi? Ben hiç düşünmemiştim. Yani burada sistemlerden bahsediyoruz ya. Şimdi equilibrium bir şey deyince ben direkt aklıma hani girdi ne, çıktı ne falan o tip şeyleri düşünüyorum. Şimdi stagnation point deyince ne diyebilirsin? Hız mesela değil mi? Akışın hızı eğer bir output gibi düşünürsen. Bilmiyorum ya. Yani karışık bir örnek. Doğru. Doğru. Unstable gibi görünüyor sahiden de. Yani stable olması için şey olması lazım. Onun civarındaki bir hava parçacığı oraya gidiyorsa stable. Yani şu örnek gibi düşünürsen. Oysa öyle değil mi? Yani hava bir şekilde alttan ya da üstten bir yerden akacak. Yani o hava şeylerin mesela suda ortaya So similarly, if you go back to the pendulum example, we said these are both equilibrium points, and obviously this is an unstable one, and this is a stable one. Okay, so that's why it is difficult to control this one, because if you don't apply any control force here, then it will by itself just fall off, right? With the slightest angular disturbance, it will just move away from the equilibrium point. So that's what I was talking before when I said for certain systems feedback control is essential, and for unstable systems or for systems unstable equilibrium point, feedback control is necessary. Without it, you cannot control those systems around those points. Okay, so as another example, let's consider an aircraft in steady level flight. So your aircraft is flying with some velocity at some angle of attack. So this is an equilibrium point, right? Everything is constant, V0. It's an equilibrium point. So if this equilibrium point is stable, then any disturbance or any change in these parameters will eventually go back to the equilibrium point. So maybe I should just write this. Then any change in do the same. If it's not stable on the other hand, then the aircraft will diverge. So it will either go down or go up, but it will just not be able to maintain that flight condition anymore. Okay, so there's some information here. Well, obviously, what it says here is obviously for aircraft, stability is a good thing. So if you consider a stable aircraft while doing a steady horizontal level flight, the pilot can just leave the controls. So the pilot can just let go of the control stick, and the aircraft will keep flying, even if there are certain small changes in the flight condition. The aircraft will keep flying straight. So that's a good thing, obviously. And if it's unstable, then you cannot do that. You should at all times control the stick, because otherwise the aircraft will easily divert from the equilibrium point. But for certain aircraft, it's a good thing. You want those aircraft are designed intentionally to be unstable, because for unstable aircraft, it is very easy to move the aircraft. So if you have a stable aircraft and if you want to perform a pull-up maneuver, for example, you need a lot of control force to do that, to initiate that pull-up maneuver. Because when you increase the angle of attack, the aircraft will normally try to go back to the steady level flight condition. So you need some force to make it go up. But if the aircraft is unstable, then with the slightest input, the aircraft will by itself try to go perform the pull-up maneuver. Okay, so for maneuverability, stability is a bad thing. So that's why some fighter jets are designed to be unstable, and F-16 is one of them, in fact. So the F-16 is inherently unstable. So because of that, it's very easy to perform maneuvers with F-16. But the downside of that is you have to apply feedback control at all times. Otherwise, you cannot keep the aircraft fly straight. Okay. Well, this definition of stability is a conceptual definition. And for system analysis, obviously there are some mathematical definitions as well. But at this point, I think the explanation is sufficient. So it gives you an idea of stability. So you know what an equilibrium point is and what stability is. So that part is sufficient for now. But obviously for engineering analysis, we have some mathematical definitions of stability as well. It's just I'm not going to talk about them at this point. Okay. Now, next, I would like to talk about the concept of state space. So this is a very important concept, and so you should really understand this part quite well. So before I start talking about it, to prepare you for the topic, let's remember what we are talking about in this course. So we have a system with some input and output. Depending on the system, these are physical variables, right? For example, if you have an aircraft, this is the control surface deflection. It is the position of some aerodynamic control surface. And the output is some variable that defines the motion of your aircraft. So this can be a certain angle, or it can be speed, things like that. And then we said that the relation is expressed by differential equations, right? So if you write down the equations for your system, you will end up with something like this. In the most general sense, you will have an nth order differential equation, which you can express in okay, so this is a differential equation, and this equation is unique. That means you have one such equation describing the relation between u and y. You cannot have two different equations that explain or that describe the same system. So if this system is linear, then you get a transfer function of the system, which is also unique. So you cannot have many transfer functions for the same system. Okay. Okay, so maybe I should just copy it from here. So in addition to, so far we talked about these transfer functions, okay? So we said if you have a linear system, then you can obtain a transfer function, and then by using transfer function you can analyze the system. You can calculate its response and go back to time domain to see how it behaves under certain conditions. And now this is a different way of analyzing systems. So instead of taking the differential equation and going to the S domain by taking Laplace transformation, we can analyze the system using the state space representation. A state space representation is a mathematical model of a system with a set of input, output, and state variables related by first order differential equations. So we take the original differential equation of the system, this nth order differential equation, and we express it in terms of n number of first order differential equations. Bunu burada diyor muyum? Instead of the equation that describes the system, we use n number of first order differential equations of n new variables okay, so we start by defining these n new variables. So if you have like a third order system, then you define 3 new variables, and these new variables should be defined in terms of the actual physical variables of the system, like the input and output variables and their derivatives. And then once we define these new n variables, we write n first order differential equations of these new variables. Bunları buraya yazayım. So these new variables are defined in terms of original system. Input and output variables, and their derivatives. And then we write n first order differential equations. And what's important here is that these new first order differential equations should be in terms of the new variables anymore, or the original system variables are not used in these new differential equations anymore. It's already written here. So these equations do not contain y, and they do not contain derivative terms. Okay, so instead of using the system variable y and its derivatives as used in the original system equation, you define n new variables. These new variables are called with letter x, and these n, and then you define n first order differential equations. And these new variables are called the state variables. These new n variables are called state variables. And then you express the same system using n new variables with n new first order differential equations. Okay? Okay, so you Şimdi bu state ifadesi dediğim gibi çok önemli bir kavram. Ve burada öğrenciler çok ilk başta bocaladıklarını biliyorum. Yani normal geçmiş senelerdeki sınavlarda ve şeylerde bu kavram biraz değişik geliyor. Ama ne yaptığımızı anlarsak herhalde bunun uygulaması daha kolay olur diye düşünüyorum. Şimdi şöyle bir sistem var. Bir tanemizde diferansiyel denklem var. Yani bu denklem o sistemden geliyor. Şimdi biz diyoruz ki buradan şöyle de yapabiliriz. Bunun yerine n tane birinci derece denklem, diferansiyel denklem x1 dat, x2 dat, xn data kadar. So if you compare the two sides here, so these are, first of all, this is exactly equal. So there's no approximation here. So whatever this equation gives you when you solve it, you get exactly the same result by solving these equations. Okay, so you don't lose anything by switching to this new representation. Here you have an n for the differential equation, which means on the right hand side you have derivative terms up to n minus 1, and you also have the derivatives of u up to some certain number m. With these new first order differential equations, you only have the new variables themselves, and there are no derivative terms on the right hand side. Here, and no y terms. So the original system variable is not used here at all. Instead, you use these new variables called state variables. the output of the original system is y. To study the original system, we need to be able to express y in terms of new state variables. Therefore, in addition to the n first order differential equations given above, we need one more equation to relate y to these new variables. And that equation looks something like that. Y is equal to some function of these new variables, x1, xn, and u. Okay, so this is how you express a dynamic system using state space equations. İkisi de, yani işlerimizi kolaylaştırsın diye tanımlanıyor. Burada direkt fiziksel değişkenler de kullanılabileceği gibi hiç fiziksel anlam ifade etmeyen fakat matematik olarak işleri kolaylaştıran değişkenler de kullanılabiliyor. Okay, so in this new representation, the critical part is defining these new state variables. And what's different here is you don't have a single option. So this representation is not unique. So you can define these new variables in many different ways. And you have different options to create these new state equations. Okay, so when you have a system differential equation, if you want to write the system in state space form, you start by defining these new variables. Bunu daha önce koyduk değil mi ya? Şimdi şurada vardı zaten. Bu aynı şekilde. Neyse şu örneğe bakın evvela yaptım onlardan önce. So I think new concepts are best understood on examples. So let's take a quick look at this example. So this is the differential equation for our system. It's a second order differential equation, and this is the transfer function that can be obtained from that equation. So we should use two new variables if you want to represent it in state space. Okay, so we will have x1 and x2, and these should be in terms of y itself, y dot, and u. Okay, so the highest order of derivation is 2. So we should avoid using that, but we can use all the other lower derivatives, y and y dot, and then we have u variable here. So u itself can be used while defining these new state variables. So the most natural choice is to relate these to the actual system variables directly. So y is the output, so we can use y itself as our first state variable. And then the second variable can be chosen as the derivative of that, y dot. Okay, so these two new variables are sufficient. Next, we should obtain state equations. These are x1 dot, equations. And remember, while writing these new differential equations, we should only use the new state variables. So we're not allowed to use the original y or y derivative terms in these new state equations. So that's the critical part. So x1 dot is equal to, by taking the derivative of this equation, it is equal to y dot. But y is an original system variable. We cannot leave it like that. So we somehow relate it to x1 and x2, and we see that it's already defined as x2. So this is the first equation, x1 dot is equal to x2. And then we need to write the second state equation. And x2 dot is obtained by taking derivative of this equation, that's y double dot. Again, this is not an acceptable equation. It contains y. So I need to refer to the original differential equation of the system, and from there I can write y double dot as u minus b over m. It's u over m, right? Is it? Minus b over m y dot minus k over m y, and I should get all these y and y dot terms. So instead of y dot, I should write x2 minus k over m, and instead of y, I can write x1. So the second state equation is x2 dot is equal to minus k over m times x1 minus b over m times x2 plus 1 over m times u. Okay, so these are the state equations. So in this case, the state variables are physical variables, right? The first state variable is the position, and the second state variable is the velocity of the mass. But it's not the only choice. So instead, we could have defined state variables as follows. For example, for x1, for example, x1 can be chosen as y plus y dot, and x2 can be defined as d times y dot, and then from here so this is also a valid space-space representation. And if you look at these definitions, they don't really have any physical meaning anymore, right? Y plus y dot. In fact, normally you cannot even add these quantities, right? Y is position and y dot is velocity. They don't even have the same physical dimensions, but yet mathematically you can define such a variable as your state variable. And then with these new set of variables, you can obtain x1 dot and x2 dot, and that will be another state space representation for this system. Okay? Aslında bu örneği de hazırlamıştım da tabii bir şekilde vakit kalmadı. So let's stop here and we'll continue next week.